Welcome back, folks, to another JLAM Bio exclusive on ACP Chemistry 2. This is video 4-3, and we're going to be focusing on periodic trends and properties. So I know we already had a little bit of a discussion about periodic trends on the periodic table, things like ionization energy, atomic radius. We're really going to dive in a little bit deeper and talk about some of those periodic properties, including ionization energy and radius, that have an impact on chemical bonding. So hopefully a pretty short video today, but let's see. Hopefully by the end of this video you should be able to analyze a variety of trends on the periodic table and determine compound formulas based off of the gaining or losing of valence electrons. A few vocabulary terms here today. We're going to focus on atomic radius, ionization energy, and the octet rule. So atoms tend to gain or lose electrons in order to satisfy the octet rule. In fact, this is the whole reason why chemicals have the ability to bond with one another. They're just simply trying to have 8 electrons in their outer shell. Now, metals tend to lose valence electrons, and this makes sense because most metals have either 1, 2, or 3 valence electrons. It's much easier to lose 1, 2, or 3 than it is to gain 7, 6, or 5 electrons. Nonmetals, on the other hand, tend to gain valence electrons. They typically have 5, 6, or 7 valence electrons in their outer shell, so it's much easier to gain 1, 2, or 3 than it is to donate 5, 6, or 7. So in this instance, the sodium atom donates the electron to the chlorine atom, thus producing a full outer shell for both sodium and chlorine. One atomic trend that we've talked about previously is atomic radius, and they can be characterized by their size. Atomic radius tends to increase as you go down and to the left. Now, the reason for this is that there is increased nuclear shielding, which causes orbitals to be smaller going across a period. So if you think about a outer shell of electrons, and say it only has 1 electron in it, it's somewhat attracted to the nucleus, but as there are more electrons in the outer shell, as the number of electrons increases, the shell gets smaller because there's more attraction to the nucleus. So as you go to the right on the periodic table, the number of electrons increases as well as the number of protons. As a result, there's a greater attraction between the negative and positive charges, which results in the atom being smaller. Now as we go down the group, higher energy levels mean larger electron clouds, according to the Bohr model, right? You have the first energy level, which is close to the nucleus, the second one, which is further out, third one, which is further out, and so on. So as a result, as we go down a group on the periodic table, the radius gets larger. So just kind of keep those things in mind and be sure you're able to understand and explain why the atomic radius changes as you move across the periodic table. Ionization energy is simply the energy that's required to remove a valence electron, and that is highest up and to the right. If you think about it, this makes sense. It's harder to remove electrons that are closer to the nucleus, so it's kind of the opposite of atomic radius, right? The electrons that are on the far right-hand corner, or top right-hand corner rather, are closest to the nucleus. So they are going to be the ones that require the most energy to remove. Those that are down and to the left are the furthest away from the nucleus and will require little energy to remove. It's much harder to remove electrons that are closest to the nucleus, and with atoms that either want to gain electrons or have the octet rule satisfied. It's difficult to remove an electron for something with 7 because it really wants to gain 1, not lose 1. Same thing with 8. If something already has the octet rule, then it's definitely not going to want to lose an electron. The second and third ionization energy is the amount of energy required to remove the second and third electron respectively. So sodium, for example, has a very low first ionization energy. It's in the first group on the periodic table, so it's going to readily lose that electron in order to satisfy the octet rule and have 8 in its outer shell. The second ionization energy is much, much greater than that, because once it's lost its first electron, the octet rule is already satisfied. To lose that second electron, it's going to require an enormous amount of energy because it wants to keep that electron to keep the octet rule satisfied. Notice the stair-step trend on the periodic table. Magnesium, which is in the second group and has 2 valence electrons, readily loses those first 2, but removing the third electron would be much, much more difficult. And this continues as you go down the groups on the periodic table. So elements react to form compounds in a way that puts 8 electrons in their outermost valence shell. This makes atoms very stable. So a lot of it is going to depend on how things bond on how many valence electrons one has to donate and how many one wants to accept in order to satisfy the octet rule. If you take a look here, you have magnesium and oxygen. Magnesium has 2 in its outer shell, oxygen has 6. So oxygen takes those 2 electrons, which forms ions, and those 2 atoms chemically bond in an ionic bond. Compound formation must be electronically neutral, so it's really easy to determine the compound based on the charges of the atoms when they form ions. Na has one valence electron, it loses it, it forms a 1 plus ion. Oxygen has two valence electrons and gains them to form a 2 minus. So it's going to require two Na atoms in order to help O reach the octet. It needs to gain 2 electrons. Sodium can only give 1. So as a result, our formula becomes Na2O, because oxygen needs 2 valence electrons and each sodium provides 1 in order to satisfy the octet rule. If you take a look on the right here, you can notice a correlation between the electron configuration and the number of valence electrons in the outer shell. The first group ends in S1, has 1 valence electron. Second group, S2, 2 valence electrons. When we get into the p orbital, it follows the same pattern. S2p1, 3 valence electrons, S2p2, 4 electrons, and so on. It's important also to make sure we understand that if we have 1, 2, or 3 valence electrons, it's going to want to give those away. Whereas if we have 5, 6, and 7, it's going to want to gain those electrons. So this plays a really important role in thinking about what kind of compounds are going to be formed based on the octet rule and based on the number of electrons that are in the outer shell. Hey guys, like I told you, short video today. Please keep these things in mind, and we will see you next time. Have a great day, guys. We will talk to you later. Bye-bye. Be sure to like, subscribe, shop merch.